So this is the last video for this lecture. We are going to look at the example that uses UnionFind data structure, but it doesn't use it just as a pure black box. It actually need to look into the UnionFind data structure a little bit. In fact, it just uses the size of the component. So the problem is from CADIS. It's called the Association for Control Over Mines. So this is a problem used in, I think, ICPC Singapore regional. So I think that problem set, they make every problem to be sort of have ACM as acronym. Because ICPC at that time was associated with the ACM, Association for Computing Machinery. So in fact now, I think maybe starting last year, ICPC is no longer associated with ACM. But it's already a very big organization on its own. So the problem description is there are at most this will be what 500,001 type of item. So the problem specification says the item type will go from 0 to 500,000, and you have one item of each type, and you have n recipes for potions. Each recipe will list the number of item types, and you need one item of each type listed in the recipe in order to make that potion. And you go through these recipes one by one, and you have as many quadrants as you need in order to make potions. So for each recipe, you can make it if you can use the unused items to make this new potion. You can also use existing ones. You can use potions you already made. If that potion recipe is a subset of this, then you can use that. You can basically pour the potion in that quadrant into this new one, and then you add the additional thing that you need. In fact, you can combine multiple existing potions with unused item together to make a potion. So if you cannot, sometimes you cannot make a potion because the items in the recipe may be already combined with items outside the recipe to make other potions. In that case, you cannot separate a potion into its ingredients. So once you mix them together, it's already mixed. So you can keep mixing them, but you cannot separate them. And the question asks us to compute the number of potions we can make. So let's look at the example. So we have 5 recipes in this sample test case. So each of the recipes start with the number that describe how many item types are in the recipe. So the first recipe have 2 items, and the item ID are 1 and 2. So obviously, given that recipe, we can make it. We just mix items 1 and 2 together. And then the second recipe also have 2 items. It's 3 and 4. So we can make that as well. So we use a separate quadrant to make this second potion with 3 and 4. So now we have 2 potions, one with 1 and 2, the other with 3 and 4. Now the third one is 1 and 5. So we already used 1 for making the first potion. And 5 has not been used, but we cannot make this potion because the only way to use 1 is to take the first potion, but that means that we also use 2. That cannot be done. That's not allowed to make the third potion, so we cannot make this one. So the fourth potion have 5 items, 1, 2, 3, 4, 5. So that we can make because we can combine the first potion and the second potion and the unused item 5 and to make this potion. So this one we can make. The last one have 2 items, 1 and 2. We cannot make it because at this point 1, 2, 3, 4, 5 are all mixed together, so we cannot make 1 and 2 again. So we can make the first, second, and the fourth. So we can make 3 of them. So At this point, I encourage you to pause the video to think about how to solve this problem. You can also go to the cont'd website to look at the problem description there. Okay, so how do we solve this problem? So we need to determine whether a recipe can be made or not. So from the items on the recipe, so we want to know where those items are, right? So we want to know which sort of quadrant they have already been put in. So what are the other items that are mixed together? So we want to check whether we combine all the quadrants that the items on the recipes are. If we put everything together, does that result in the item in the recipe? So if it includes the extra item, then that cannot be done. But instead of actually checking extra and this and that, we can just count the number of items, so long as we can ensure no item is counted more than once. So we can use the UnionFind data structure. So for sort of when we pour quadrant together, we will use the union. When we see a recipe for see an item, we will use find to find the group that it is in. So we need to keep track of all the unique groups that the items on the recipes are in. So if we have 2 items on the recipe that belong to the same group, we don't want to count that twice. But suppose we keep track of all the unique groups that the items on the recipe are in, then we only need to add up the size of those groups. And if that size is the same as the number of items in the recipe, then we can make it. Then that means there is no extra, because this putting everything together covers all the items. And if I have exactly the same number of items, that means it cannot have anything extra. So that's the idea. And this is the Java code for solving this problem. So we start by creating an object using the UnionFind class, sort of we discussed in on the earlier lecture. So actually there was a bug in the UnionFind code. So if you watch the video earlier, you may have noticed that. I fixed that on the slides. So if you look at the slides, the bug has been fixed. So I find the bug when I work on this problem, and its answer is incorrect. So I figure out there's a bug there. So we create this UnionFind with because it says at most there's this number of items, so that's the side we initialize it. So we first read in the number of recipes, and initially answer is 0. So this is how many recipes we can make, and then we loop through all recipes. For each recipe, we read in the number of items on the recipe. At the same time, we will use the size to keep track of the total number of items if we merge all the quadrants those items currently are in. So in order to avoid counting the same quadrant twice, we will use a hash set to sort of keep track of what are the unique groups. So then we read in each item. For each item, we read in store it in X, and then we will find the group ID of that item, Y. So then if this this hash set already contains this, then we don't need to do anything, because we are trying to count the total number of items in all the quadrant we have found. So if it contains, that means we have already counted that quadrant, so we can ignore that. If it doesn't, then we will add that Y value into the set of quadrants, and then at the same time we will increment the size by the size of the group for Y. So this items is the UnionFind class, and the size array store the size of the each distinct subset. So once we've processed all the items, at this point we check whether size equals m. So size basically will be either greater than m or equal to m. If it doesn't equal m, then that means we cannot make this recipe, because when we put everything together, there's something extra. So that's not the potion specified by the recipe. So then we'll just simply continue. Otherwise, we will increment answer by 1, and then we need to merge all the different quadrants together, because now we are making this potion. So essentially, depending on yeah, so I guess there's a different way to implement this. So what I did is I will each time I will sort of union x and y, and x will loop through all possible quadrants, but the first one there's nothing to unify to union with. So I put the initial value of y at -1. So if y is -1, we simply assign x to y. So otherwise we will union x and y. So that's all. So in fact, after this for loop, the next line is simply to print out the answer. So that's the code for this mind control. So it uses UnionFind. It just we need to actually directly access the member for storing group size, because that information we need to use. Okay, so finally, these are the hints for the homework problems for this week's problem set. So we have 3 problems. So 2 of them are so lost map is a pure minimum spanning tree. The interesting part about the problem is to figure out this is actually a minimum spanning tree. And lattice problem is a problem that can be solved with UnionFind. Millionaire Madness is a problem that can be solved using many different ways. So I think that's one of the reasons that it's an interesting problem. So you can use the UnionFind to solve it. You can use the Prim's algorithm to solve it. You can use a bisection with connectivity, and the connectivity part can be done using either BFS or DFS or UnionFind. So there are many ways that you can solve this problem. So that's all. Have fun solving these problems.